Let's derive a relationship between torque and the angular momentum. So first we'll start off with the fact that rate of change of linear momentum, change of linear momentum is equal to net force acting on the object. So we have dp by dt is equal to the net force acting on the object, right? This you guys know. Now, what will I do is I will take a cross product on each side with R. So we have R cross dp by dt is equal to R cross summation of Fi. What is this quantity? This is nothing but your torque, right? And also I'll use additive identity and write this. I'll explain why. I'm going to write plus 0 is equal to your net torque. Now, can I write 0 as 0 will also be equal to dr by dt? Can I do that? Why? I can do that, but why? See, dr by dt represents what? Velocity. And momentum and velocity are what they are, or what is the angle between them? Yes, they will be parallel to each other, as P and V are parallel to each other. This implies the cross product will be equal to 0. So basically, I have net torque is equal to P R by dr by dt, sorry, plus R dp by dt. Happy? Now, can I use the derivative UV product rule? The product rule, actually, UV rule or product rule. Can I rewrite this as dr by, sorry, dr d by dt, wherein you are taking the cross between R and P. I can do that, right? If I differentiate this, I'll get back this. Can you see that? Okay. So basically, if I happen to compare on comparing with your force is equal to dp by dt, what do we have if I happen to compare this? If we compare this and this, what will happen? What is that we are looking at? So your net torque on the LHS is equal to force, and your R cross P is equal to your P. So what can you tell from this? Your R cross P should play the same role as should play the same role in rotation, actually. Role in rotational motion as that of P place in your translation motion. That is R cross P is your angular momentum of the particle. And that's that. Okay. So yeah, sorry, I got distracted. I went ahead. So we are looking at this result. Okay. Sorry, I again missed. Where else? Yeah, that's it. So we are looking at this result. So we can see that your torque and angular momentum have this relationship. Actually, sorry, I kind of didn't conclude the answer. So basically, torque, your net torque, is equal to dL by dt. That's your final answer actually. So this is a relationship. What is this? This is nothing but same as this. Rate of change of momentum is nothing but force. Rate of change of angular momentum is your net torque. As simple as that. Okay. Sorry, I didn't explain much. I just kept writing the math. So now let me explain it actually. Let's make sense out of it. So let me take up an example. See, we have a feeling about the bullet and stuff. I keep using this example talking about a bullet which is moving and a truck which is moving, right? And how scary each of this scenario is because of certain reasons. Okay, and we understand that if any one of this is moving at whatever velocity and mass they have, and if we have to change their any kind of values of say momentum, it is not easy. We need to apply force, and this force is proportional to the momentum change in momentum that we need, right? We have seen this is one of the laws. Okay, similarly we have torque related to your angular momentum, change in your angular momentum. If I have to change a lot of angular momentum, I need a lot of torque. As simple as that. Common sense. If something is already rotating, I need a lot of torque to stop it, provided it has a lot of mass and it has a lot of angular speed. If something is heavy and stationary, I need a lot of torque to make it rotate. If it's small and light, then I need less force to make it rotate. Right? So basically, whatever we saw in our linear motion and anything and everything related to linear movements and the cause and the effect and so on and so forth, right? Acceleration, momentum, forces and everything, net force and everything. A similar map can be applied to here as well, to this angular world as well. So an obvious conclusion is that force can be measured by looking at how fast we want the momentum to change. Similarly, torque can be measured by looking at how fast we want angular momentum to be changed. Do you guys agree? Right? This should be commonsensical. And how did we start the derivation? We started the derivation with telling that, you know what, I know momentum, rate of change of momentum is force. And we know the relationship between force and all of this, angular momentum and everything, right? So what did I do? I multiplied with R. Okay, sorry, I missed again vector form. I took a cross product on each side with R. And you know, R into force is your lever arm, and your cross product between R and the force and everything. is nothing but your torque, right? So that with that basic understanding, I went forward with the derivation. And here I ended up with taking r dp inside the bracket, dr by dr cross p by dt through a simple mathematical tool that is known as additive inverse. If you guys don't know about zero is additive inverse. That is, I can add 0 to anything and mathematically things are not changing. So with that fact, I was able to rewrite this expression and come to this conclusion. That is, a torque is rate of change of angular momentum with respect to time. Okay, so you have to write this, an important result and a very commonsensical result, and the derivation is quite simple. So we'll be using this now. We'll derive few things based on this.